Hello everyone. Today we're going to introduce you the fluid properties in SimCenter MSim. Our learning objectives are to know what fluid properties are used in hydraulic simulation and what are the equations behind these properties are. No matter what kind of fluid system model is to be built, the fluid properties are always the first item to be considered. So all necessary properties used in SimCenter MSim will be detailed in the following slides. Additionally, the phenomenon of aeration and cavitation will also be introduced, as they are quite important in most of hydraulic applications. Speaking of fluid, or to be more specific, hydraulic oil, there are many terms associated to the description of hydraulic oil. The properties of hydraulic oil contains density, compressibility, viscosity, thermal conductivity, specific heat, and so on. Also, some parameters are also important to check the fluid status, like saturation pressure, boiling points, etc. However, in hydraulic system modeling, we will use only a few of them. There are three essential properties to handle dynamic effects in hydraulic networks. First, its fluid density. It's defined as mass divided by volume, and it describes the mass characteristics. The second one is bulk modulus. It's a measure of stiffness of the fluid. Some fluid are more compressible, so it's less stiff. The last one is viscosity. It's a measure of resistance when fluid is moving, and it is caused by shear stress. These three properties are the most important ones in hydraulic simulation when using HYD library components. The thermal-related properties, such as thermal conductivity, specific heat, and thermal expansion, are not considered in HYD library, but in thermal fluid libraries. The air or gas content in fluid plays also an important role on fluid compressibility. The saturation pressure and vapor pressure are two critical parameters to handle aeration and cavitation phenomena, which has influence on fluid bulk modulus also. As it's able to put a fluid in a constant volume, supposes that the fluid is compressible. The compressibility of the fluid is defined in MSim with the bulk modulus, and the formula is shown below. Bulk modulus is defined by the pressure and volume variations. Making an analogy with mechanical systems, where a reduction of the length of a spring leads to an increase of its reaction force. This definition leads to the hydraulic stiffness of a volume V. It equals to bulk modulus divided by its volume size, and apparently is a nonlinear stiffness. Another important fluid property is density. Density is defined as the mass per unit volume. Rho equals mass divided by volume. The SI unit is kilogram per cubic meter. Also, fluid density is a function of pressure, temperature, and the type of fluid. Now it comes an important note, the dependence of density and bulk modulus. Why there is a dependency between fluid density and bulk modulus? Because we need to respect the mass conservation law in the hydraulic system if there are no mass changes in the circuit. The density value at different pressure and temperature is linked to variation of bulk modulus, so we need to know exactly what the dependency between these two properties is by listing the equations behind. First, let's check the Taylor's development of fluid density around the reference operating point, assuming there are small variations of state variables. Then what we get is the equation at bottom. The residual terms can be ignored. In HYD library, the thermal effect will not be considered, so that means the third term in this equation can be ignored. Then what's left is the term describing the compressibility effect. In a closed hydraulic circuit, no liquid mass should appear or disappear. Then dm is equal to 0. And since the temperature doesn't change, so we can derive that dV divided by V equals to minus d rho divided by rho. From the isothermal bulk modulus definition below, we can replace the dP dV with rho divided by d rho. Then we get the relationship between bulk modulus and density. The last one is fluid viscosity. Viscosity is a characteristic of liquids and gases, and it can be interpreted in motion through internal damping. The definition of viscosity was first given by Newton. The absolute viscosity mu is defined as shear stress divided by shear rate. The absolute viscosity is also called the dynamic viscosity. Another term of viscosity is called kinematic viscosity, nu, which is the ratio of dynamic viscosity over the density. It's used in many equations and is easily measured by any viscometers. Please also note the viscosity value is constant only in simplest fluid property option. For the rest of fluid property models, it's a function of the pressure. Now we need to introduce two important phenomena, aeration and cavitation. The fluid used in the hydraulic system is usually aerated, and the presence of air or gas in the liquid can have unpleasant consequences on the fluid compressibility. So that's why we need to understand them and try to set the fluid property parameters correctly to have the same system dynamics in the model than in the real system. In SimCenter MSIM, you can use air-gas content to set the volumetric percentage of air or gas inside the fluid. The saturation pressure is a pressure above which all the gas is dissolved. Below this pressure, there is a law describing the quantity of free air or gas as a function of pressure. Another important phenomenon is cavitation. Cavitation is the formation of vapor bubbles inside the fluid due to the falling of fluid pressure below its vapor pressure. We show in the graph the difference between boiling and cavitation. Boiling is the transformation from liquid to gas due to increase of temperature. Cavitation is transformation from liquid to gas due to decrease of pressure. One example of cavitation is given in the pump example. Cavitation occurs at the inlet of the pump due to pressure drop at the filter and to the suction of the pump. Let's compare the two phenomena. Both are related to pressure level. When the pressure is higher than saturation pressure, there is only dissolved air in the liquid. If the pressure decreases and lower than saturation pressure, the dissolved air will be released as free air. If the pressure keeps decreasing to a level lower than vapor pressure, then air bubbles as well as vapor cavities will be formed. Cavitation happens. During this short lesson, you have learned what fluid properties are used in hydraulic simulation, what is the dependence between bulk modulus and density, and what are cavitation and aeration phenomena. That's all for this short lesson on fluid properties introduction. Thanks.